We are going to do a technical presentation of Guillotina. And, well, mostly we yesterday explained why we created it. And I was saying all the time, we are going to explain about async IO, we are going to explain what was the problems that we were facing when we were doing the framework 2 years ago. And this is the talk that we are going to go through all the different points that we had pain doing using Plone and using ZODB and using rel storage. So we are going to explain all the decisions we needed to make in order to build a framework that fulfills our requirements. First of all, if you don't know, I'm Ramon Navarro. I have two companies, Isker and Stagify. I'm from Foundation member, and I'm Catalan, and this is the demonstration in Catalonia last week.
Hi, and I'm Nathan Van Gheem. I work at ONA as principal engineer. I'm Plone Foundation member, and I don't really play guitar anymore. I just felt I needed that because Ramon always talks about playing music, and I'm American. Normally wouldn't say anything about that either, but you know. Yeah, so we're just going to try to go topic by topic to talk about some of the different areas that we used to tweak performance and create a framework for scaling to a lot of data in Python. And some of those are, I guess I can repeat them, but you can read them as well, but async IO, and then just the design of the database, caching and lifecycle management, indexing, file storage, and queues. So the first thing we'll go over is async IO. I guess I just want to stress that async IO is really important for Python and the web in general going forward. The threaded approach, we'll just talk about how async IO is different than a threaded app. In a threaded app, when a request, an HTTP request comes in, it's assigned a thread, and that thread is active through the duration of the request. And then once it finishes, the thread is returned to do another request. So you're limited to the number of simultaneous connections for the number of threads that you have on your application. In Python, that usually means 2, because Python doesn't perform very well with lots of threads. The best way to deploy Python is with 2 threads per process. So you can just keep doing more processes to scale, which is fine, but then you don't have any memory sharing or anything like that. But moreover, it's just it's the differences between how you block on your application. So if you have the threaded approach, a request comes in, and then you communicate with, say, PostgreSQL, and maybe it happens to be a slow query, and you're blocking for 3 seconds to wait for that query to finish. Now that thread is consumed for that whole 3 seconds while that query is communicating, and that Python's not doing any CPU, it's not doing anything at all, but it's still blocking, and it's preventing other people from being able to have their requests serviced. So that's the threaded model of request per thread, and that's Django right now, that's Flask and Pyramid. And so think about how this applies to situations where you're communicating with lots of services. You're sending things to a message queue, you're communicating with Redis for caching, you're doing OAuth for authentication or any kind of authentication or authorization provider, you're doing S3 for file storage. Like any of these services, they're all over like HTTP or some kind of TCP connection, and now you're blocking on communication. If there's anything slow in any of those services, you're blocking, and you're not doing anything. And so this is where async IO is useful. Like it's non-blocking network IO now, and you can communicate with all these other services, and while you're communicating, there's very little overhead in maintaining that connection, and you can really push the performance of Python where you weren't able to before. And moreover, just think about the context of microservices. And even if you think microservices is crap, the reality is you don't have to be microservices. You're still using a lot of other services. You're connecting to other APIs in a number of ways. You're at least using like multiple database layers, or like most applications you develop now are not just database only. You're going to be communicating with something, some API, maybe an authentication service or something. So like this is going to be a problem if you have any sort of substantial load. And to illustrate this even further, I guess I do have an example of some code to show like how this can be. This is going to be an example of a CPU-bound application versus a network-bound application. And so like one of the, I'll back up a little bit because I forgot to explain the downside of async IO. So async IO is a single-threaded, it's a single-threaded approach to running your application. So one process, one thread, your event loop, which is running the async code on, is only on one thread. So if there's any CPU-bound code there, it's going to block on CPU, like because no other code can run at the same time if you're executing CPU. It's single-threaded. It's really important that you don't block on CPU. Whereas threads, if you have high CPU load, you can switch threads every once in a while, and you won't ever have a situation where you're blocking all other code from running. So that's one downside. So if you know you have CPU-bound code, you have to be careful about it. In async IO, there's a way to run CPU-bound code in a thread pool. So you just have to know what you're doing. But anyways, this is to demonstrate. This is some code that just crunches numbers for half a second, and we can see how it behaves. And the regular async IO approach is 2 requests a second, and the threaded approach without setting any threads, 2 requests a second, behaves the same. Async IO with the executor, that's what I was talking about, how you can throw CPU-bound code in a thread pool. That does slightly better than a threaded application with 20 threads, which you don't really want to do, but that's just to say you needed to try to scale it further with a single process. So the problem isn't that much different with the CPU-bound app. But if you go to a network-bound app, and this is the same sort of thing, we're just connecting to a service, and that service is just a service that is delaying for half a second before it returns, which is an async IO service, of course. And then the difference is this, and this is only bound by the number of concurrent requests the library was using per host. So it could go further. It's just that was some arbitrary limit they had on the number of concurrent connections per host. And the threaded app is abysmal for the performance. Yes.
Just to say that async IO it's amazing for network, but there is a lot of other input-output things that we have on our computers that the async IO is also really helpful. We are not using at Guillotina specifically because most of the things is kind of a REST API and it's mostly network communication, but we are using also a lot for example, accessing the disk with long operations that you need to do on the disk. Or I'm sure that there is a lot of input-output communications with devices, with the kernel, that you could build drivers for async IO in order to be also on the event loop. So everything that you need to wait, async IO, it's amazing. And sub-processing, yeah, you just start a new process, and we have processes that start a lot of different processes and wait for them. Meanwhile, they are doing other things, serving HTTP, so we can monitor the processes that are running. All this input-output, it's so easy with async IO. And there was another thing is Python delivers with a standard event loop, a basic one, that it works really well for most of the cases, but there are other implementations of event loops, for example, the UV loop, that it's much faster than the standard one, that it's the same as Node.js. No? And there is also the Tokyo event loop, that it's written in Rust, that it's also really fast. So the system is so pluggable that if you really need this extra 20% of speed, you can even switch the event pool to something that is much more performant. It's me? Sorry. So, the async I/O was the main important thing that we needed to Gheem. So it was the first thing that we decided that were going to happen. Then the second thing that we decided is that we needed a database as a place to store. No, we started storing things on a file system, on folders, and well, it was okay, but we needed some kind of more strong way of storing with transactions. That so there is a lot of databases that offers that, and we went on to understanding how Rela storage works. No, we say Rela storage has been there for a while, it's been growing, so we want a pickle system, what we can copy, and we went to check Rela storage, and we decided a design that it's a bit inspired with Rela storage, also with that database that Gheem built, NewDB. Yeah. So Guillotina is traversal. So there is main nodes that you have on the tree, and these main nodes are registries on a table, which this makes easy to be able to do a select on the table and to do a dump and to get all that objects out of it. Then we decided that we don't have enough with a row with a byte field on Postgres to store all the information that we want from an object, because an object maybe can grow up a lot and we need to include extra information. So we copied the concept of annotation from Plone, and we decided to have annotation registries that links to the node object. So if you do a select on a Guillotina database, you will see rows that are the node objects, the basic nodes on the tree, and nodes that are annotations from to these node objects. Then, of course, we are a tree. So on the SQL structure, we needed to define a way of defining pointers even to the children or to the parent. In our case, we decided to point to the parent. So each row has a pointer to the parent or to the node that it's an annotation for. Why we did that? Because of course it's much easier to avoid to check conflicts, because you are only pointing to one. At the beginning, when we started to do the design, we didn't not use the JSON-B indexing from Postgres. So we decided that by then we are going only to store the pickle with a byte field on Postgres, and then indexing it's for another system. We are microservices, so Guillotina is only taking care of storing with transactions the main objects and the notation objects. So well, these are some of the configurations on Postgres that we have on right now. Mostly, it's a simple one table, one big table with all the information. So each database that is mounted on a point of the tree, it's at that table, and you can have multiple tables and mount on different endpoints on Postgres, on the URLs of Guillotina. Then there is a lot of foreign keys that make sure that you cannot delete. If you delete the children, all the parent, all the children gets deleted. If, for example, you want to do a post with the Plone REST API to create an object, and you define which is the ID, checking if that ID exists, it's a simple operation because there is a primary key that doesn't allow to have different IDs for the same parent. So the database itself provides consistency.
But related to that, you don't know until you try to commit if there's a conflict in this way, because we didn't want to. So as we'll go through more, it's like you need to cut out all possible places where you're going to do a lookup. So If on like when you're doing a post to create a new object and you have the ID, and then you at that moment you check to say, hey, is there an ID of this already exists on the database? That's always going to be a lookup to the database. You always need a connection to the database in order to do that. So we're like, no, we'll just wait until we actually succeed and let the database do the constraint check for us. If the database gives a conflict error, then we kick it back out and it's a conflict error and the client can handle the 409. We're a REST API, so they should know how to handle 409s, and that's kind of how it's handled.
Thank you. Great. So another thing that is important that we use a lot, and we are really thankful that Postgres can give us to go fast, is the sequence number. So the transactions ID is it's really important that are sequential, and Postgres itself offers us a sequential ID that it allows us to have a sequence number for doing that. There is two things that this architecture makes. There is a lot of things that makes this a bit complex, but two major one. One is that we lost the history. No, the ZODB kind of append only that you are storing all the information on each transaction, so you can go on time and decide how far you can go. We don't have history, so we have a snapshot of actual situation. We can implement versioning on top of the objects by the data model itself, but the transactions. We support what Postgres supports as transactions, and we have the snapshot of the database. Of course, if, as the previous talk explained, you define a specific snapshot on time on the database, then you can go back if you don't remove the history. Another thing that is difficult is the relation of children and parent. The children pointing to the parent. Ordering is really complex because we really need to. You cannot store the order on the children. You need to store the order on the parent, or you can store and then you need the list. Or if you store the order on the children, then you need to index that properly.
Yeah, so if you guys are familiar with how this is done in Plone, they store, if ordering is like they're storing a complete list of the order of the folder on the parent. So every single time you add an object or you like change the order, it's modifying the parent object. And but we don't do ordering. I mean, the Guillotina CMS thing does ordering, and it's just setting an attribute. And so it's like a fuzzy, like pseudo enforced ordering. So like, you're still only writing to the child, and that's the safest way to do it, where you can actually not have like huge performance implications with it. Anyways, there's more on writing to parents.
There's a lot of things. No? So just to see an image is always, after explaining all these things, an image helps a lot, no? So this is an SQL from a select of a table from Guillotina. You see that there are two specific registries, the DDDDD and the 0000. A 000 is the root object, so it's the first object, and DDDD, it's the trash. So when we are deleting something, we are making the pointer of the parent of that element to point to DDDD. Why? Because we discovered that the reference integrity foreign key deletion trigger, when we were deleting kind of folders with millions of objects, were kind of shutting down the database. So we decided to do the deletion on batch operations. So we point the object to the DDD, and then there is a batch job that cleans up everything. You will see during some slides that we talk about vacuuming or batch jobs to clean up. We need to do a lot of these things. We cannot do everything in real time because we want to answer fast and we want to provide integrity.
Yeah, so like if you do a delete of a really large folder in Plone, it might take like 30 minutes or something like that, because it's doing all of that in one single transaction, making sure that transaction is synchronized across all the other transactions that are happening, and then hopefully it actually works. So all we do is set this attribute, and all of our cleanup, reindexing, all that stuff is in an async task or in a queue, and that's how we manage doing large operations that affect a large amount of data at a time.
Yeah, some other differences with Rala storage is that of course, we have the object ID, is the ZOID. I am a romantic guy, so I choose to name it ZOID for romantic reasons. You may understand. The transaction ID, this is the sequential number. State size, this is also a romantic name, to store the size of the byteum. Part is a field that you can create an adapter, so each object can define in which partition is stored. This is used for what's been explained also in the talk before, that Postgres 11 supports partitioning, Postgres 10 also, 11, no? Supports partitioning, so you automatically do a partition, you can partition your database table with multiple subtables, and using this attribute to define in which partition you want to store it. Resource, a boolean just to know if it's a main object or it's just an annotation. Off, in case that you are an annotation. The all transaction ID is for the cycle of commit, the two-phase commit. Parent ID is the pointer to the parent. The ID is the real ID, and this is different, for example, from I think on Rel storage, or maybe it's the type, that you have the real ID that appears on the URL. Then the type, the real type from Guillotina, that we have. JSON is the serialization that we want to use for indexing in case that we use Postgres catalog, and a state that is the pickle.
Let's keep it on there. One second. One other thing about the ZOID is you can see from row 3 to 6, all of the ZOID keys start with 824. That's for if you're using something like Cockroach, we have Cockroach DB support as well. In order for it to distribute the data, it does key sorting, and you want to have your data near each other if you're querying it. So if you didn't have this sort of key storing, which allowed Cockroach to put chunks of data on the same node, it would be having to do the queries between Cockroach DB nodes and synchronize those queries, and it can be really slow. So that's the reason why the ZOIDs are structured that way.
Yeah, the 3 digits are the parent first 3 digits, and each children gets the 3 digits from the parent also besides its own ZOID. So everything gets ordered on Cockroach. Yeah, and we already explained a bit about that. Deletion, it's complex. Synchronize, making sure that you have a clean system, it's complex. And right now we have 2 systems of auto-vacuuming. By default, Guillotina tries to create an async IO job to clean the database, but we also added an option to disable that, so you have an external job that does it manually. No? Okay, now caching.
So we use Redis to facilitate our caching, and then an in-memory cache. I mean, I guess in that respect, it's a lot like the way ZODB caches objects. We just have an LR. I guess I say that next to it. We have an LRU cache that's pretty fast and written in C, and we have cache keys for all operations that are done on the database. And then, so we set the in-memory cache, and then we use Redis to coordinate invalidations between Guillotina application servers. And yeah, so that's kind of it. And optionally, it can also push cache out to other application servers as well. Depending on your load, that can be actually a negative performance hit, because that can put a lot of pressure on Redis to push out all that data if you have a lot of writes going on. So how I usually deploy, or how we deploy, I'm sorry, is we just use Redis for invalidating cache across the application servers, and everything else is just straight in-memory cache then, and we don't push out any new values with Redis. Yeah, so the L2 cache would be a reference to the Redis actually storing cache of the pickles. So like I don't use that, but it is supported, and if you don't have a write-heavy system, it can be helpful. Yeah, so in the design, we just want to, you always just want to reduce the amount of lookups ever. So everything that you, every operation that you can potentially do on the database should be cacheable, and you shouldn't ever need to be doing any types of operations that require lookups. So like we had mentioned before, when we insert into the database, it's like it can produce 409s that the client just needs to deal with, and that's because we don't want to have, we want to optimize for the normal case instead of the edge cases, because that's what most of our requests are, and then the client can have some of the logic to deal with those edge cases. Yeah, I guess I kind of already said that. Yeah. Okay. And Ramon's good.
Okay, so one of the cool things that Async.io has is the option to have tasks that run in parallel. In parallel meaning that they are waiting that there is some input-output to be run, because we cannot use more than one CPU. And one of the things that we have is requests feature. So you have a request and you can add tasks or functions or operations or whatever you want that is going to be done after the request is finished. So that helps, for example, for indexing, or you want to call some audit log or do whatever you want. And well, it's so easy that you just get the execute global function of Guillotina, and you do after this request, call this function with these arguments. And it will be called after the request has already been delivered to the client. So it's not, so that you can really have operations that work after the request has already been finished by the client in Async.io. It's like the pre-post. We also have pre and post commit hooks, so you can. Yeah, we are also romantic on that. So you can do whatever you want before a transaction or before a commit or whatever, but they are done before the request has been delivered to the client. So whatever you do there, it's going to make the request a bit longer. Whatever you add on after request, it's never going to affect the request time. And then we have another interesting thing that we needed to develop to make this kind of Async.io jobs work better. It's a pool and a queue of tasks. That means that we call something async utilities, also for romantic names. Utilities are single items that are running in memory that does wherever you want. And we Guillotina out of the box delivers us with a queue that we can queue tasks there. I don't know. Connect to this service and say that I'm alive every 5 minutes, or call Celery and do whatever, or call this queue system and do whatever. And so the queue and the pool, it's like before, you just get the pool and you say run this can run forever and it's never going to block. Well, it needs to be something that it's Async.io. If it's CPU bound, will block all the system, of course. But you can just execute wherever you want there, short, long, whatever. And these Async.io utilities that we have a lot. We have for caching, for the indexing, for the working pools. We have a lot. There is a lot right now. Yeah, transaction mechanism. So. As Nathan said before, we don't want to access the database because accessing the database it's slow. So we are trying to demurrate as much as possible accessing the database. So we have a traversal system that goes through all the objects. If they are in cache, we don't need to access the database. We go through the security. We validate whatever JSON Web Token you have. If we don't need to access any service or you need to access a service, you access it. And then we look for the view. Well, there is some more things on the traversal, but you look for the view. We start a transaction at the moment that we are going to execute the view, and then we execute whatever is inside, and we close as soon as possible when we finish the view, the rendering. So we tried always to demorate as much as possible, and we also want to try to be as smart as possible with read-only and write transactions. And we are using something that we are really proud, is the get, the HTTP verbs. So, you know, we have get, head, post, delete, patch. So why don't we use these verbs to define on advance that the connection is read-only or is write? So what we do is if you do any head or any get or any head on Guillotina, we even don't open writing transaction. We just do a read-only transaction that we are not going to commit. For sure, you cannot write to the database on any get or head operation. And we use the pause, the get, add the pause, the patch, and the delete, and then we open transactions. So that helps us because then you can tune that you have, for example, a slave of Postgres that it's only for read operations, that all the gets go there, and then you avoid overloading the main database. You can do a lot of things if you have this kind of tooling, so you can define read operations and write operations. Yeah, another important thing is that we have our concept of what's a transaction that we are reusing on our tasks, and we are using now in 3.7 the context bars to store these transactions. But a transaction in Guillotina is not a transaction on that database. So we start a Guillotina transaction at the beginning of the request, and we end at the end. But as I said before, we try to make as far as possible, as small as possible the transaction, and if we don't need the database, we even don't open the transaction. Yeah, finally, in this block of lifecycle management, kind of what's happening, we have an option that is called xdebug. If you call Guillotina and it's enabled with a parameter that is called xdebug, you get really interesting debug headers where you can see the timing of each of the phases that you have on the traversal and the performance of the cache, the memory cache, and how many queries you're doing to SQL. It's a really interesting tool too. So when you finish, okay, this call, where I'm spending more time, no? Oh yeah, we also support, we have packages for Prometheus to send metrics to Prometheus and on a statsd. So you can deliver all this information to see if there is any problem. Indexing, that's me. Okay, we will go faster because we are running out of time. So indexing, it's a really complex problem. And if you want to, we are storing the pickles on the database, no? So we wanted to make something that it's fast, but it's also synchronous. So the first approach that we went is to index things on Elasticsearch. What means is that we have a process that extracts the indexing information and sends to Elasticsearch completely out of the transaction. That makes that the index may be out of sync with the main database. So you may have objects that are not indexed or information on the index that is not on the object. But it was a really fast first approach. And it fixed it. Well, maybe we were losing some information on the index. Maybe it was late. If you, for example, now if you try to use Elasticsearch on Guillotina and you want to use Volto, you create an object and you go to the folder and you don't see until 1 second because Elasticsearch needs 1 second to index that information. So yeah, this is synchronous even from a Guillotina point of view, even from Elasticsearch or whatever you're using to communicate with Elasticsearch, it's a problem. So you need to have 2 jobs that are every some days going through all your data, making sure that everything is indexing or re-indexing all this information. We will Andy explained it before, a good solution for this problem with Kafka, but we will explain something if we have time. Then we decided to create also transaction-type indexing. So it means that there is as we are storing on JSON beyond Postgres, that means that it's on the same transaction, and if the transaction fails, the information is not stored on the index. It's really goes really fast. It's scalable using JSONB. We have indexes for all the fields that we use to index. The problem is that the full text search is not as powerful as Elasticsearch, and if your needs require Elasticsearch, then that you need Elasticsearch. And yeah, so there is API to initialize the indexing, to repopulate the indexing, to delete the indexing. It's not only a container. A container is what Plone should be a site. In Guillotina, it's an index. You can define that any folder is a subindex. You can define multiple subindex for each folder of your site if you want. And yeah, file storage, storing files, it's a bit easier than indexing. And we are lucky that there is a lot of services that provide this kind of backend in order to support storing files. We have S3, Google Cloud Storage, and Minio, that it's an on-premise S3 that you can install in your Kubernetes cluster. You can also use database, but as we said before in the talk before, it's not recommended to have large volumes of blob files on Postgres. Oh yeah, we are building a new driver for Guillotina to store also on the file system if it's needed. But what's important is that it's async IO. Any file coming in and out of Guillotina, even because it's coming from the storage to the client, or from the client to the storage, it's a stream. It means that we are chunking, wherever, if you're sending all together or with TOS, we are chunking with buffers of 256 or up to 4 megabytes of bytes, and we are sending this information to the service and the other way around. So I remember that in Zope, maybe a long time ago, I needed to download files locally and then return to the client. It's so easy with async.io to have this buffering of input-output, meanwhile you're doing other things with other tasks on the same thread. Yeah, it's also important to know that if you're using S3 or Google Cloud Storage or Minio, you need to have a vacuuming in case there has been some unsync information between the storage and Guillotina. Yeah, I'm going to go really fast. As is the Sync.io, queues are really friendly with the Sync.io, so we support AMQP. Mostly designed when you really need to ensure that the task is being done, so you need to have an ECK, this is being done. You have Kafka support, that it means that you can even logging, use sequence for indexing, and being able to have a consumer that indexes that on Elasticsearch, or to also assign tasks, more kind of a streaming service. And then you have NATS and Stan, that is the best of AMQP and the best of Kafka together. Sorry, I'm using that. It's yours.
Yeah, some other things that we found out in tuning Guillotina is, well, here we don't got a lot of time, but anyways, be careful with reference cycles. So objects that end up referencing through a chain of references of objects themselves. So like, it's really hard to garbage collect, or for Python to garbage collect reference cycles. It takes like a lot of reference or garbage collection attempts before it actually gets it out of memory. Also in async IO, each task is like this object that doesn't get cleaned up immediately. And if there's ever some exception, even if it's like, I don't know, like a conflict error or whatever it might be, that exception, usually an exception object usually wraps the local context of what happened in that exception in it, and so that might have references to objects inside of it, and that might not be cleaned up right away because that task, even though it may have been finished, the object that holds the information about that task hasn't been cleaned up. I don't even know the rules behind when, I think it's like a weak ref. I don't know the rules behind when that actually does get cleaned up in async IO, but there's like this weak ref dictionary of tasks or something that doesn't always get cleaned up. and that can be a lot of memory sitting around potentially. There's also the profile, built-in profile in Python that's really nice that you should use to know profile like CPU intensive code. And then there's this really nice library called Line Profiler, and that will give you the full time of every single line of code that you just decide to profile in this. So like you can look at a line and then that took so many microseconds, and then you can go into like what function that called, and then you can see it all split into like where inside of that function, like you can keep going down and see like where the time was spent, and it's actually time, not CPU time. So this will include if you're like connecting to a database and that database is slow or whatever. This can be really helpful to identify slower parts of your code. Yeah, and Guillotina comes with built-in support for both of them. There's the -- line profiler command option, and also just profile command option. And then so you can kind of see, this is the line profiler output, but if you want to actually profile a function, you have to add that @profilable decorator, and then once you use this, it will register that this needs to be profiled. And this is line profiler output, though. It tells you line by line how much time was spent on every line. I think
that's all. Thank you. Any questions?
Hi. I noticed you turn off the auto vacuum on PostgreSQL. Oh, okay. So you're auto vacuum. Okay, no, because it's not safe. Okay, you answered my question. Thank you.
I'll answer it a little bit better. Yeah, because when we delete, we just mark an object as being deleted, and so like there's a application vacuuming process where we're actually going through those and doing going all the way, going in a shallow way and deleting them individually instead of relying on referential integrity to clean them all up. Because referential integrity, if it's a substantial amount of objects that need to be cleaned up, can like take just gigabytes of memory and destroy it.
Hi. Maybe this is a crazy question, but how much SQL are you really using in Guillotina? I mean, if it is just a little part of SQL, for performance, you can bring more and more using directly or writing and reading from files using the Postgres libraries, for example. Better would be to use a database built with async.io directly, so it can be plugged in on your application. This would get the best performance, but I don't know if it exists. So I'm asking if you, when you did your research, if something like this can happen or exist.
Yeah, I guess at the time, Postgres was really by far the best option. There was this really nice async PG library that's been async.io. That's an async.io driver for Postgres that's really fast. And even when we started this, not all databases had async.io drivers. And Postgres is really fast. As long as you use it correctly, it's really fast. And then if you're going to use a database that spoke HTTP, there's like overhead with that, and they might be able to scale horizontally, but then like regular operations aren't necessarily really fast. And there's no database that's just async.io. In the end, it's still Python. It's not going to be as fast as like C or Rust or C++ or Go. But we use Python because we like it, and there's other benefits to using Python. So this is fast in Python. We mean Python fast. You know, you can still do a lot with Python. Instagram uses Python in async.io. They're pretty big. It's just a matter of choices and trade-offs.
Other question? Comments?
By the way, Instagram also uses Postgres. So
You use build-out, right?
no,
No, what do you use then?
just pip.
Oh, okay. Because I saw like /bin in examples. I saw /bin in examples.
/bin.
Yeah.
Oh, I just the virtual environment.
Yeah, okay, I thought that's the one.
Nice try.
Other question? Oh, okay.
Hi. Sure, I agree with the lookup prevention schedule because that takes time. But the actual issue there is race conditions because first you select, then you update.
Yeah, so we have a transaction ID that we look up to make sure that it's a safe operation.
So that would work in your case specifically, yeah. But there could still be another thread or another operation that will insert, and then you get a 409 because it will be invalid.
And then you get another 409 or something, yeah.
Yeah,
So you might have
so-
to do multiple 409 checks, yeah.
So the actual client needs to take care of that anyhow.
Yeah.
Yeah. Cool.
Yeah, retries, yeah. We have built-in retries too for database conflicts. So I mean, yeah, like just like ZODB has retries, it's kind of the same way in that respect, but the client still needs to handle it in some cases.
Exactly.